Okay. I'll be presenting in English. I will be presenting in English, and I was kind of worried because I thought. Okay. Okay. Let's see. And I've turned on subtitles. I hope they work. But okay, here we go. I'm Keita, founder of Kotoba Media, working on geospatial data wrangling and product development research, in addition to contributing to Rust open source libraries. I spend more than 90% of my time in Rust these days. Recently, a patch of mine that fixed optimized writing in PM Tiles RS, I think Brandon was talking about that earlier today, was released. A little about me, I was born in Tokyo. I was raised in the United States, and I'm living now in Yakushima. It's a small island about 60 kilometers south of the southernmost point of Kyushu Island. So Tokyo is actually really cold for me. Yeah, and my interest in GIS started when I first got my iPhone. It was iPhone 3G, I think. You could only use SoftBank, and it was really slow, but whatever. But it had GPS in it, and I was able to make a GPS-based app, and it was really fun. So I really liked that, the bridge between the physical and the digital worlds. And so we don't have much time today. So I'm going to be showing a bunch of sample code, and there's a link here. I'll also be showing this link later, and it's also in the timetable, so you can look at that if you want. It has all the sample code and links to the projects that I will be talking about. Okay, so what is Rust? It's a programming language, but these are some adjectives that we commonly described Rust. You can see like safety, memory safe, fast, efficient, usability, modern, expressive. But so today I'll be talking about how this translates to actual code. And so here's a very simple example. Or maybe I can put a laser pointer. Okay. Yeah. So we have a vec here, and a vec is short for vector. That's what it's different from like vector data, but it's basically an array or list. And you have a bunch of points here, and you can convert these list of points into one single multipoint, and then you can get the centroid of that multipoint, and then you can print the centroid like this. And then this is from the GeoJSON crate. You can turn that into a GeoJSON string. And so this is what it looks like when you run this code. And this shows how expressive Rust can be. This code looks almost like JavaScript or TypeScript, but it's running as fast as a C or C++ program because it's compiled and basically doing the same stuff. Okay, so now onto safety, which is a big Rust selling point for me. For me, safety is equal to performance. I've written my fair share of C in the past, but especially in multi-threaded code, you can have really weird bugs when you're sharing memory and stuff like that. And Rust completely eliminates this kind of these errors with a couple very strict rules. So yeah, I call this fearless concurrency. So if you're trying to do something wrong, the compiler will tell you, and it won't let you compile. Of course, there are other logical bugs, like, for example, a lock order inversion that can cause a deadlock, but data races are completely out of the mind. So you can focus on what's important in your code. We have a rich ecosystem of libraries. They're called crakes. Here are some examples, especially with the Geo community. We have a GeoRust organization in GitHub, and we have a lot of things like Geos bindings, Proj, GDAL bindings. I'll talk about rstar, and also each of these formats, they're optional, so you put in the format that you need for your project, and then you can not include excess code in your library or app. And this is a question that I got a lot about Rust, is it about the learning curve? And the learning curve is pretty high. Before I was doing Rust, full time, I did a lot of TypeScript, and it looks the same. So it was pretty natural. But there's no escape hatch to JavaScript, which was pretty hard. Like in my mind, I had an idea of what I wanted to do, and I just wanted to do it, but the compiler didn't let me. But right now, ChatGPT is your friend here. Just put everything into ChatGPT, say, I want to do this, and this is how it works. Yep. Okay, so now I'm going to talk about multi-threaded processing. Just like JavaScript, we have async and sync. So async is cooperative, sync is preemptive. We use as OS threads here. Async is normally for I/O, network I/O mostly, and sync is for CPU work and file I/O. You can mix this async and sync code, but we usually use messages to communicate between them. And since most GIS work is CPU bound, we're doing calculations on the CPU, I'll be focusing on sync mostly today. So here is a sample example of a fan out in pattern. So first here we have a generator thread. We are just generating a sequence of numbers. This is from 0 to n items. It's 1,000 here. But in a real app, you would be reading from an input source or something like that. And then in our processing thread, we boot up these workers here. Let's see, n workers is the amount of CPUs we have available. So we boot up, maybe if you have 10 CPUs, then you boot up 10 workers. And it takes inputs from the input. And then it sends it off to the output thread. And then so the output thread, this is a single thread thing. And this is usually because if you have multi-threaded output, then records can get out of order, stuff like that. This kind of manual pattern is very complex, but it gives you a lot of control. However, there is a way to make this a lot easier, and it's this crate called Rayon. And so basically, what I had before here, this is 3 different screenshots. All this is combined into this one small thing. And this, you can see that it has the 0 to 1,000, and then this into par iter part. This does all the heavy work for Rayon's boot, and then this for each with, it just does everything here. So this is very expressive, and I usually recommend using Rayon for 80 to 90% of your multi-threaded uses, if you need. But sometimes you need to, do some customization. Okay. Now I'm going to talk about geospatial. You'll be fine with the GeoCrate. The GeoCrate, I showed you the Centroid calculation before, but it has all those kinds of calculations. There's an R star crate for a in-memory spatial index. I'll be talking about that next in the examples. For raster processing, you probably need the GDAL bindings. I've shelled out to GDAL commands before just because they're easy. There is a WGPU crate for doing operations on the GPU. I haven't tried that yet, but that's another story for another time, I guess. Okay, so here's some concrete examples of how I'm using Rust in my open source GIS projects. So this is MOG XMLRS, and which needs a better name, I think. But it processes Chizu XML files. These are from the Ministry of Justice, and they cover cadastral parcels of most of Japan. The input files are about 95 gigabytes compressed, and the canonical Python implementation takes a long time. It takes more than 8, 9, 10 hours to do all of Japan. And with this tool, it can do it all in 1 hour on my computer. So this is the basic pipeline. We take the input XML files, we unzip them and parse them in parallel, and then we have the output in serial. It's basically what I showed before with the fan out in thing. So the parsing stage, we use an XML crate to parse the file, extract what we need into our internal representation, something like this. And then we use proj4rs, a pure Rust proj4 port, to project the coordinates into WGS84. We build the polygons. There was an earlier talk about PostGIS topology. These Chizu XML files are in topologies, so we have to parse them out into polygons, and then we send it off to the next stage. The output stage, We support GeoParquet, Flat GeoBuff, and GeoJSON. So we use a Rust pattern for polymorphism. This is called trades. So we have a writer trait. You can see we have a new output. This makes a new file, add XML features, and then flush. This is just to close the file. And so this is what the writer code looks like. So there is no GeoJSON or GeoParquet or Flat GeoBuff specific code in here. All of that implementation details are done in the GeoJSON writer, something like this. So this is a pretty common pattern to do this kind of stuff in Rust. Okay, and here is another tool, MVT Wrangler. This has to do a lot with PM tiles. So basically what this does, it takes a PM tiles archive of MVT vector files, it transforms them, and then it outputs a new PM tiles archive that's modified. And you heard about PM tiles and protomaps before, but what I use this tool for is to create a modified set of the protomap space map, which you heard about before, tailored to use in Japan. For example, there are a couple sensitive areas. I think everyone knows what I'm talking about. A couple sensitive areas where in the OpenStreetMap database, there are features and names that may not be appropriate for all uses in Japan. So what this does is they filter out those areas, those features, and make a new tile set based on it. I run this process every day in GitHub Actions, limited to the Japan region. It takes about 20 minutes. It's basically, because GitHub Actions is a bit slow, like you can do it on your computer, maybe it takes 2 or 3 minutes or something like that. And this is the, This is the stage, and I'll be explaining it a little bit more in detail. But so we have the input, the filter file here. It's just a regular GeoJSON file, and it has a very simple, it looks like MapLibre filters. It has a very simple filter syntax here, and here's a couple examples. So we have a filter here where it removes any feature in the POIs layer, removes any features in the buildings layer, and here's a very complex example, but yeah. So after we compile all the filters, we start the processing. And what we do is we iterate all the reference tiles. We send all these tiles onto a channel. Think of the fan in out in pattern, and then fetch the tile data from the PM tiles archive. After we fetch the data, we send it off to the tile processing channel. And then so the tile processing channel, we use Rayon to do this. And so actually channels are really cool. I showed you an example before where we use the receive function from the channel to get messages off the channel. But here we're using it as a iterator. So we can see this in Rx here. We do into iter and then par bridge. So what this is doing is we have the in Rx channel, and first we're turning it into an iterator, Rust iterator. And then this par bridge part, this turns it into a Rayon thing. So it's very easy to compose these workflows inside Rust and using different kinds of libraries to do all sorts of things. And I will now talk about getting the filters. So these filters, they have geometries. So for example, this removes any feature in the POIs layer. This doesn't apply to the whole tile set. This only applies to where this GeoJSON feature intersects. And so how we do that is we have an r* index. And because the r* index is a bounding box index, this is the same as PostGIS or any kind of geospatial index. We search for intersecting filter features with the target features bounding box. After we get the bounding box matches, we perform a high resolution intersection match. This is here, this candidate geometry.intersects. This is also from the GeoCrate that I was talking about before. And then, so this is for when the bounding box intersects, but the geometries themselves don't. And then we run the filters on the tile. And then in the output, PM tiles for optimal reading performance, tiles need to be ordered in the output. Parallel processing means that we can't guarantee the order. So what we do is we just reorder them on the output side to make sure they're output in the right order. We don't have much time, so I'm going to skip through these. But I will. This presentation will be uploaded. The link is in the timetable, and you can take a look at it there. Okay, so yeah, summarize. Rust can give you very powerful tools to take advantage of all the CPU cores available in your machine. I got a new CPU that had lots of cores, and it can completely saturate it. It's great for doing lots of parallel calculations, which is really suited to GIS applications, especially tiled stuff, because you can do everyone independently. Yeah, thanks for listening. Don't forget to get the example code. あとでこの同じ内容で日本語でも多分 YouTube で配信すると思うのでX をフォローしてフォローアップしてください。はい、ありがとうございます。
はい、ありがとうございました。では5時間あるので、会場の方からご質問ある方いかがでしょうか。じゃああちら。
Is this microphone working? Okay, there, great. Sorry, so I need to ask the question in English. But so thanks for creating all of these tools around PM tiles. And I know the focus right now is on modifying an existing archive, so going from one tile archive to an output archive. But in Rust, so what's the status of actually generating vector tiles? Because right now, all of the tools, such as Tippecanoe, Planetiler, they're either C++ or Java.
Right.
And one thing that would be very exciting is to be able to create vector tiles in Rust. So can you talk a little bit about the status of that?
Yeah, sure. So as far as I know, there aren't any tools right now, but it is technically possible. So what I'm doing with my this MVT Wrangler thing, I'm actually parsing every single vector tile, and then I am reprojecting all of those coordinates into WGS84 coordinates, and then filtering it based on that, and then putting it back into a vector tile. So it should be technically possible to do that, generate them from scratch, basically. Yeah.
Okay, cool. Thank you.
Yeah.
もう7名ぐらいいけそうですけど、いかがでしょうか。大丈夫ですかね。お願いします。
質問も日本語でも大丈夫です。
英語でもいいように簡単な質問だけ考えてたんですけど、ラフトを使ってて一番大変なとこは何ですか。その GIS 関連に関してラフトを使うことで、なんか一番今回割となんかいい部分を語ってもらったと思うんですけど、大変だなって感じるところは逆に
そのジオの、クレートに多分修正はされてると思うんですけど、前の方は結構特殊な、ジオメトリーとかちょっと壊れてるやつだと完全に、パニックっていうかアプリが落ちるっていうことはよくありました。でその場合は、ここに最初の方には言ったんですけど、そのジオスのバインディングがあるので、ジオスだとポストグレと同じくやってるので、ここら辺ですね、GOS とか GDAL のバインディングがあるので、それを使えば抜け道 っていうか、そういうエスケープハッチ的な感じで、対応はできたけど、まあ、最近は良くなってると信じたいです。はい。
ありがとうございます。
ありがとうございました。ではお時間になりましたので、以上とさせていただきます。
はい、ありがとうございます。
ありがとうございます。Thank you for your presentation.
Thank you for listening.